Hello, everyone. Welcome to our session, What's New in Tizen? I'm Hyunju Shin from the Tizen platform team. Tizen platform is now powering a wide range of devices, such as smart TV, monitors, digital boards, and various home appliances. Today, we will explore its new features and capability. Let's get started. First, I will talk about PenWave and the AIAvatar framework that bring new AI-powered features. I will also cover the unified memory profiler and how Android on Tizen is expanding the ecosystem. After that, my colleague Hyogwoo Park will explain the optimized web engine and support for new hardware architecture RISC-V. Now, I'd like to introduce PenWave, the new handling engine added to Tizen. Let's watch a demo video to see the key features of the PenWave. The engine provides an infinite canvas, allowing you to expand your ideas without boundaries. Our advanced rendering ensures every stroke is smooth and natural. Whether you are sketching, writing, or designing, you can freely switch between various tools to express your idea. With PenWave, you can easily edit your ideas. The engine supports editing both selected area and individual strokes. Additionally, you can load images in different formats and export your creations as SVG or PDF files. In developing the PenWave engine, we face three key challenges: ensuring high quality, maintaining low latency, and creating a developer-friendly interface. Let me explain how we address them. First, high quality. To achieve superior visual quality, we used vector-based approach. This ensures every stroke, line, and shape remain clear, no matter how much you scale it. To deliver high-quality content efficiently, we maximize the use of GPU acceleration. The CPU generates spline points to define curves and send them to the GPU. The GPU uses these points to generate complex meshes through the geometry shader, after which rendering tasks are performed. With these approaches, PenWave reduced CPU load by 23% and decreased memory uses by 51% compared to traditional RAS-based engine. Second, low latency. Real-time responsiveness is crucial for natural drawing experience. To minimize hardware overhead when processing pen events, predicting future events is essential. We've developed an AI-based prediction technology that significantly improves accuracy compared to traditional mathematical models. Along with AI event prediction, we applied GPU front buffer rendering and Tizen-specific window direct rendering technology. As a result, we improved latency by 56%. Finally, to make it easier for developers to utilize hand-drawing features, we provide the pen canvas view, enabling you to focus on creativity. Canvas view, which hides the complex implementation details. It's incredibly simple to use, enabling you to focus on creativity rather than technical challenges. Explore PenWave coming in Tizen 9 and create a variety of apps. The next topic we will introduce is the AIAvatar framework. In today's digital era, as technology becomes more integrated into our daily lives, AIAvatar play a crucial role in enhancing user experience. By combining visual and auditory elements, AIAvatar create richer and more engaging interactions. Imagine creating your own conversational AI avatar. To achieve this, we need various AI features. First, it's essential to have a language model as the brain, which interprets what the user says and generate appropriate responses. Next, text-to-speech provides avatar's voice. Then lip syncing ensures the avatar's lips move in sync with the audio. Lastly, sentimental analysis express emotions and behavior through facial animation and body movement. By combining all these elements, we can create an interactive AI avatar. However, building your avatar service from the ground up would require significant amount of effort. Tizen offers an AI avatar framework that simplifies the process of creating avatar service. This framework includes a range of features to bring your avatar to life, such as 3D character rendering, multilingual TTS, and lip sync animation. Additionally, it offers a flexible interface that allows you to replace the built-in AI solutions with external ones. This flexibility expands the capability of AI avatars to suit diverse environments and requirements. Now, let's watch a demo video that shows how the avatar expresses emotions.
How can I help you?
You might say, "I'm so sad, please comfort me." Then the language model generates a response. And sentimental analysis processing begins. We use a small-scale language model to detect the emotion in the response. Based on the identified emotion, the avatar's facial animation is rendered accordingly. Avatar provides human-like presence that bridge the gap between users and technology. We recommend trying out AIAvatar framework to deliver a richer experience for users. Now, let's dive into the enhancement in Tizen Memory Profiler. Tizen is designed to use native languages like C and C++ to ensure optimal performance even on low-end IoT devices. Since Tizen 4, native API have also been available in C#, allowing developers to take advantage of the .NET environment. Previously, profiling managed memory and native memory required separate tools. Now, Tizen offers a powerful feature that enables tracking of both types of memory together, providing valuable insight for optimization. The Tizen Memory Profiler has two main features. First, live monitoring. This feature shows real-time memory usage during application execution. It tracks the physical memory uses and monitors various events. This monitoring is done without any performance overhead, allowing developers to quickly and easily spot memory issues as they occur. Second, recording and analysis. This feature allows you to record a specific period of the application lifetime and analyze memory allocation information in depth. You can set both the recording period and the minimum memory allocation size to be analyzed, minimizing profiling overhead. Now, let's watch a video that shows how to use the memory profiler. The live monitoring feature displays the real-time memory uses. The gray area indicates native memory uses, and the blue area represents managed memory uses. Event icon indicate points where the application lifecycle changes and user events occur. You can easily check the difference in memory uses over the selected time interval. The trash can icon indicates when garbage collection has been performed. By selecting the icon, you can review detailed information. The recording feature is useful for examining more detailed memory allocation information. For the recorded section, you can review all memory allocation course tags, which include both native and managed area. This feature will be essential tools for optimizing memory uses in your Tizen application. Be sure to take full advantage of the Tizen memory profiler. Next, let's move on to discuss Android on Tizen, a technology we are advancing to further expand the Tizen ecosystem. Android on Tizen is an innovative feature that allows Android applications to run on Tizen platform. This means users can seamlessly use existing Android applications on Tizen devices without any additional modification. It maximizes compatibility by supporting a wide range of Android applications. To seamlessly run Android applications on Tizen, we execute an Android container on the Tizen host. Additionally, we've developed core component integration between both environments. To maximize graphic performance, we developed GPU driver compatible with the Tizen graphics buffer. This allows the Android container to directly access GPU for native-level graphics performance. We've also integrated the package manager and application launcher from both Tizen and Android, enabling seamless installation and launching of Android applications on Tizen devices. This graph shows a comparison of GeoBenchmark score between the Tizen host and the Android container. The results indicate that the Android container achieves nearly identical graphics capabilities with the Tizen host. We've also applied several memory optimization techniques to minimize the memory footprint required for running Android applications. As a result, we've significantly reduced memory consumption, ensuring efficient execution of Android applications. Tizen will continue to evolve to support an even wider range of applications in the future. That concludes my part of the presentation. Now I will hand it over to Hyegu Park. Hyegu, the floor is yours.
Thank you. Hello, everyone. My name is Hyegu Park, and I'm a software engineer at Samsung Research. Today, I will introduce two key innovations, which are lightweight web engine and RISC-V support in Tizen. So let me start by introducing our lightweight web engine. At Samsung Research, we are independently developing various lightweight web engines. And unlike heavier performance-driven engines like Chromium, our focus is on creating web engines that are light and efficient. And this ensures that our web-based services run smoothly across a wide range of Tizen devices. Currently, we are developing 3 web engines, and first one, LWE for web browsing, and Escargot for JavaScript, and finally, Walrus for WebAssembly. And among these, LWE is the largest project. LWE integrates both Escargot and Walrus internally, combining them into a unified web engine. So our lightweight web engines are developed with 4 key features in mind. The first one is web standard. We aim to support a wide range of the latest web standards. So by supporting these standards, we can ensure compatibility for various web-based services. The second one is memory efficiency. Since Tizen services run on a variety of devices, many of which have limited resources, so it's really crucial to use as little memory as possible to ensure functionality in resource-constrained environments. The third one is performance. While memory efficiency is a priority, performance cannot be overlooked. It's essential that we maintain a good balance between saving memory and delivering a good, smooth user experience. And lastly, cross-platform. Our goal is to support a wide range of hardware and platforms so that our web engines can ultimately be used beyond the Tizen. And now I will introduce each web engine one by one. First one is LWE. LWE is currently included in Tizen under the package name Lightweight Web Engine. It supports core web standards such as HTML5, CSS3, and JavaScript. Additionally, it is compatible not only with Tizen, but also with Linux and Windows environments. And this graph on the right side shows a comparison of memory usage between LWE and the Chrome browser based on measurements from several sample web apps. And from this graph, using Chrome's memory consumption as a baseline, LWE uses on average just 52%, roughly half the memory. And this demonstrates the impressive memory efficiency of the LWE engine. Next, let's talk about Escargot, our JavaScript engine. Escargot is being developed as an open source project and is now publicly available on GitHub. It supports the latest JavaScript standard, ECMAScript 2024, which was released this year. Escargot can be used not only on Tizen, but also across various platforms, including Linux, Android, and others. We've continuously applied memory and performance optimizations to Escargot and have even published 2 research papers on our findings. On the right side, you can see a graph comparing the memory usage of Escargot and V8 based on JavaScript benchmark test. And V8 is the JavaScript engine used in Chrome browser. And similar to the LWE results, when using V8's memory usage as a baseline, Escargot consumed only about 24% of the memory on average. And this also demonstrates its highly efficient memory usage. Lastly, let me introduce Walrus, our WebAssembly engine. To briefly explain, WebAssembly is a new web standard language that allows applications written in various programming languages to be converted into WebAssembly and run in web environments. Today, WebAssembly is being used not only on the web, but also across many other platforms. Our Walrus, like Escargot, is being developed as an open source project and is available on GitHub. It currently supports WebAssembly version 1.1 and is continuously evolving with new features. And since WebAssembly is often used to handle heavy workloads in web environments, so performance is critical. To address this, we have implemented a just-in-time compiler in Walrus. The JIT compiler translates WebAssembly code into machine code at runtime, significantly boosting the overall performance. Our JIT compiler supports various architectures such as x86, ARM, and RISC-V. This graph on the right side shows the performance impact of the JIT compiler on several WebAssembly sample codes. Using the performance without JIT as a baseline, we observed an average performance improvement of 5.1 times after applying the JIT compiler. And our Walrus continues to evolve with ongoing feature additions and further JIT optimizations. Our LWE is also continuously adding new features, and among the newly added features are WebGL and WebWorker. WebGL is a technology that allows browsers to handle 3D graphics, enabling compatibility across various platforms and utilizing GPU acceleration for fast graphic processing. And as you can see in this demo video, LWE runs the sample WebGL app smoothly, demonstrating its capability. And another feature is WebWorker, which supports multi-threading in the browser. With WebWorker, tasks can be processed in the background or in a non-blocking manner, improving the overall performance of web applications. In addition to WebGL and WebWorker, LWE continues to develop and incorporate a variety of new features to enhance its functionality. Now, LWE is running various services across multiple devices, and one of them is Bixby service. Bixby is a voice assistant service integrated into Samsung Smart TV and Galaxy phones, and our LWE is used to power this service. In this example, you can see the screen on a smart TV where the user asked Bixby for the current weather using the remote control. When this happens, an LWE pop-up appears on the smart TV, displaying the weather information retrieved from Bixby. Going forward, LWE will continue to be developed and optimized to support a wide range of services. Finally, let's discuss RISC-V support in Tizen. RISC-V is an open source instruction set architecture that provides flexibility in hardware design. It allows for customization and scalability, making it suitable for a wide range of computing devices. The project of RISC-V support in Tizen has made significant progress this year. Currently, we have developed Tizen platform that runs Tizen sample apps on a reference RISC-V board. And these sample apps include native apps, web apps, and C#-based .NET apps. The RISC-V porting of Tizen has been successfully completed, and we are now publishing daily Tizen images for RISC-V on the public Tizen download site. In addition, we have ported 1,169 Tizen packages to the RISC-V platform, and over 40,000 Tizen APIs have been tested and verified to ensure compatibility. For the RISC-V architecture, we are using the Vision 5.2 board from Star 5 as our reference for verifying RISC-V operation. We have also ported the necessary tools to support the RISC-V build environment and have established the infrastructure to release daily Tizen images for RISC-V. The SDK environment for building and testing native web and .NET applications is fully prepared, and we also provide support for both CLI and IDE tools as well. Now, Tizen supports multiple languages for app development, such as native, web, and C#. Among them, web and C# apps run in real time on their respective language runtimes. To support the RISC-V, each language runtime must be compatible with the RISC-V architecture. The .NET runtime, which is the runtime for C#, supports multiple architectures and operating systems. However, supporting new architectures requires modifying several modules. Specifically, the .NET runtime includes a JIT compiler that generates machine code from intermediate code during runtime, which means we had to develop a compiler backend to support the new RISC-V architecture. At the time when Tizen decided to support the RISC-V, there were no plans to support the RISC-V in .NET. Therefore, we took the initiative to release the porting of the .NET runtime to RISC-V. Based on .NET 8, we started contributing code to add RISC-V support. Since last year, we've made over 230 pull requests and contributed more than 30,000 lines of code, achieving over 99% of unit test pass rate. And I want to emphasize that all of these contributions have been led by Samsung, and development is still ongoing to implement additional features and ensure stability. The .NET runtime we developed has been integrated into the RISC-V Tizen images, allowing C# apps to run seamlessly on the RISC-V platform. And you can see this in action through a RISC-V Tizen TV demo that we've prepared just outside of this room. In addition to developing the RISC-V support for the .NET runtime, we also applied several performance optimizations. Specifically, we implemented optimizations to improve the app's startup time. And as shown in this graph, we were able to reduce the startup time by an average of about 60%. And that concludes our presentation, and thank you for your attention.